You know, when you look around, it seems like everything moves in its own way. But what if I told you there's a hidden code? A set of rules that governs everything from a planet orbiting the sun to the phone in your hand. Well, that's what we're doing today. We're going to crack that code and dive into the brilliant and, honestly, pretty simple laws of motion that Isaac Newton figured out centuries ago.
Okay, so here's a weird one for you. Shaking out a dusty carpet, launching a massive rocket into space, and flicking a striker in a game of carom. Sounds like the beginning of a bad joke, right? But believe it or not, there's a deep physical connection between all three. Just stick with me, because by the end of this, the answer is going to feel so obvious.
All right, so here's our game plan. We're going to tackle this in 4 parts. We'll kick things off with what I like to call the stubborn law. Then we'll get into the simple math behind every push and pull. After that, we'll see how the universe always keeps things balanced, and we'll wrap up with the incredible power of momentum. Let's get into it.
So, first up, Newton's first law. I call it the stubborn law, because really, that's all it is. It's about how every object in the universe is just a little bit, well, stubborn. It likes to keep doing exactly what it's already doing.
I mean, think about it for a second. You flip the switch on a fan, you cut the power completely, but the blades don't just freeze, do they? Nope. They keep on spinning, slower and slower, until they finally stop. Why is that? The power's gone, so what's keeping them going? This little everyday puzzle is the perfect way to understand our first big idea. And the answer, in one word, is inertia. It sounds kind of technical, but the idea is super simple. Things don't like to change. If something's not moving, it wants to keep not moving. If it is moving, it wants to keep moving. You could almost think of it as the universe's natural state of being lazy.
This is the law in a nutshell. It's really two sides of the same coin. An object at rest stays at rest, and an object in motion stays in motion. But, and this is the most important part, that's only true unless some outside force comes along and messes with it. That little unless changes everything.
And this is a fantastic example. In carom, you flick that striker and bam! It smacks into the bottom coin of the stack. That coin goes flying, but what about the rest of the stack? For just a split second, they barely move. They just drop straight down. That's inertia in action. The stack resisted that sudden forward motion and wanted to stay right where it was.
Okay, so inertia is all about resisting change. But, things do change. We push them, we pull them. So what happens when a force actually wins? That brings us right to Newton's second law, the formula that tells us exactly how that change happens.
So let's picture this. You've got 3 blocks, all different weights, tied together with a string, and you pull the whole train of blocks with a steady force. The question is, how fast is this whole thing going to speed up? It looks kind of messy, but thankfully, Newton gave us the perfect tool to figure it out. And here it is, the one and only F equals ma. Force equals mass times acceleration. This little formula is the engine of physics. It tells you that the more force you use, the more acceleration you get. But it also tells you that the heavier something is, the more mass it has, the harder you have to push to get it to accelerate at the same rate. So, let's put it to work. First things first, since all the blocks are moving together, we can just treat them like one big object. So we add up the masses. 1 plus 4 plus 2 gives us 7 kilograms total. We already know the force is 50 newtons. Then we just rearrange the formula a bit. Acceleration equals force divided by mass. So we just plug in the numbers. 50 divided by 7.
And boom, there's our answer. The whole system moves together, accelerating at 7.14 meters per second squared. What looked like a complicated problem becomes a pretty simple bit of division, all thanks to F equals ma.
So we've got that forces cause things to accelerate. But here's another one of Newton's huge insights. Forces never, ever act alone. They're not lonely. They always come in pairs.
This is one of those classic physics head-scratchers. You're in a boat, you stick a long pole in the water, and you push backwards on the riverbank. And yet, your boat shoots forwards. How does that even work? A backward push creating forward motion? It feels wrong, but it's actually the perfect example of Newton's third law. And here's the key to that whole puzzle. This famous line right here. For every single action, there's an equal and opposite reaction. You literally can't push on anything without it pushing back on you, with the exact same amount of force, just in the opposite direction. No exceptions. So let's look at that boat example again. The action is the person pushing the pole backward on the bank. Simple enough. But here's the magic. The reaction is the bank pushing forward on the pole and the boat attached to it with the very same force.
The forces are perfectly balanced, but they're acting on different things. One pushes the bank, which is too big to move, and the other pushes the boat, which isn't.
All right, so we have inertia, we have F equals ma, and we have those action-reaction pairs. But what happens when things actually run into each other? What are the rules for a collision? That brings us to our last big idea, momentum.
Think about it. Two billiard balls cracking against each other. Two cars and a fender bender. Anytime two things collide, the physics is all dictated by one really powerful fundamental rule. It's a rule that the universe seems absolutely obsessed with following.
And that rule is the conservation of momentum. Now, momentum is basically an object's amount of motion. It's how much mass it has times how fast it's going. And this law says that in any collision, the total amount of momentum you start with has to be the exact amount you end with. It doesn't go anywhere. It's conserved. This is exactly how physicists tackle a collision problem. They map it all out. They figure out the total momentum before everything hits by looking at the mass and speed of each object. And because they know that number can't change, they can work backward to predict exactly how fast each object will be moving after they hit. It's like a perfect accounting system for motion.
So here's the main takeaway, the really critical point. In a collision, momentum doesn't just vanish. It's just passed around. It gets transferred from one object to another. One ball might slow down, but the other one has to speed up to make up for it. It's a perfect trade.
So there you go. That's your basic toolkit for understanding how pretty much everything moves. You've got inertia, which is why things are stubborn. You've got F equals ma, the recipe for making things change. You've got action-reaction, the rule that forces are a two-way street. And you've got conservation of momentum, the law of every crash and collision.
Which brings us all the way back to the beginning. Shaking a carpet? That's inertia. The dust wants to stay put, so it falls out of the moving carpet. Launching a rocket? Pure action-reaction. The rocket pushes gas down with massive force, so the gas pushes the rocket up. And carom? That's a beautiful dance of inertia and the conservation of momentum every time the striker hits a coin.
See? These laws aren't just for a physics class. They are literally happening all around you, every second of every day. So the next time you see something start moving, or stop, or bump into something else, just take a second. Now that you know the rules of the game, where are you going to see them being played?